There we go. It's my honor to introduce Cristoph. Actually, Cristoph, I don't remember your title, so if you can remind it to us before you start, that would be great. Thank you so much for joining us. Feel free to start whenever you're ready.
Yeah, thank you very much for inviting me. So, can you see my screen now? Yeah.
Yes.
Okay, great, good. So the title is Rigidity in Conformal Field Theory and Vertex Algebras Beyond Rigidity. And it's based on some work with some people. And I've tried to present you a picture, and I also want to spend quite a bit of time on some explicit examples. So it's a topic at the interface of categorical structures and vertex algebras. And as you know, I know a little bit about categorical structures, but I'm not an expert on vertex algebras. So I had to resort to the help of experts. And you can obviously see who are the experts here in this range of collaborators on vertex algebras. And they should be credited, given credit for most of the insights. But let's start with rigidity and explaining what rigidity in the tensor category is. So I think the language of tensor categories or monoidal categories is by now a lingua franca which connects many fields. So I'm not going to explain what a tensor category is, but let me remind you that a right dual of an object in a monoidal category is another object. Well, it's not necessarily different, but it can be different, together with two morphisms, an evaluation morphism into the monoidal unit and a co-evaluation. And of course, we are introduced to this structure very early in our lives, typically in the first or second term in the linear algebra course, when we learn that if we have a vector space, then we have a dual vector space. Well, and the dual vector space contains linear forms. They can be evaluated in vectors to give scalars. And then, not really completely in this language, we learn that there is also a co-evaluation which gives us a map in this sense. And this exists for finite dimensional vector spaces. And for finite dimensional vector spaces, we can identify this. And there is a distinguished map which takes a scalar and sends it to the scalar times the identity. So this is something we learn very early on. And then, so I should explain why in this context here, the dual is on the left and on the right. Well, that's due to the famous zigzag relation. So if I'm writing the co-evaluation, the evaluation in this sense, so I'm always reading morphisms from below to above, and the co-evaluation in this way. So this goes from V into V dual, then the composition of evaluation and co-evaluations gives the identity. That's one of the equations you have. And the other one is that if you have this here, that's also the identity morphism. Well, then maybe you learn about rigidity in a course on finite dimensional Hopf algebras and finite dimensional modules over them. And essentially that's already almost a cheat, because Hopf algebras are tailored in such a way that you keep as much structure as you want from the category of finite dimensional vector spaces. You keep the tensor product, and you keep also the rigidity by introducing the antipode. Well, and usually you require well, if C is a right dual of C dual is a right dual of C, then C is a left dual of C dual. So there is a notion of a left dual, and the category is called rigid if all its objects have a left and a right dual. Well, this has important consequences. So the tensor product of a rigid abelian category is exact. That's because there is a duality gives a functor which is monoidal, and this is very deeply built in the graphical calculus. So if you look at X tensor Y and you do the duality, you want to be able to draw it in this way, and then you are getting Y tensor X. And so we have here a very strong structure, in particular implying that the tensor product is exact. Now, a little thought already tells you that this is not completely natural if you look at real life algebraic structures, and I would say vertex algebras are real life algebraic structures. So there is a nice tensor product theory, which you know much better than I do, due to Huang, Lepowski, and Chang. And this gives the tensor product that's right exact, but it is very easy to find examples where the tensor product is not exact. So in a sense, if we take the sound algebraic structures first, we should go beyond rigidity. And that's the topic of this talk. And the talk will give you some results, and in the end, I will share some confusions. So the question that I want to put forward here is, what is a good notion of duality, a good categorical notion of duality for vertex algebras? And so in order to get a feeling what these structures are, we go to something that's way simpler than vertex algebras, because they are too complicated for me. And here it's late, so I have to start with something very simple. So let's work over a field, and let's take a finite dimensional K algebra. And in fact, all modules will be finite dimensional, all vector spaces will be finite dimensional. Then you learn in class how to define the tensor product of bimodules. Well, that's the co-equalizer, where you equalize the right action of A on B and the left action on A on B twiddle. That's textbook knowledge. That's, as a co-equalizer, this gives a right exact tensor product. And this is, in a sense, the simplest realization of a monoidal category. Now, is there a duality in this case? Well, if you think about linear algebra, you take the linear dual of a bimodule, and then you endow it again with the structure of a bimodule. And well, actually, if this is an A1, A2 bimodule, then it naturally becomes an A2, A1 bimodule. By formula, everybody who has worked with simplest aspect of representation theory will immediately understand. So we get a functor from A1, A2 bimodules to A2, A1 bimodules. And due to our assumptions, finite dimensional, this is an involutive functor, contravariant and involutive. Now, the point is that this functor is usually not nicely compatible with the tensor product. So let's look at this. So if I take here G on a tensor product, I'm not getting G on the tensor products independently on whether I'm exchanging here the order or not. Well, let's take an example. If I take M to be the regular bimodule, so A as a bimodule over itself, that's the monoidal unit. So that gives us on the left-hand side G of N, but on the right-hand side, I get a dual, and I have to tensor a dual with G of M. And a dual is typically a bimodule that's not the same as the bimodule A. And tensoring with a dual is a famous functor. It's called the Nakayama functor. So in general, this module and this module will be different, and it's well understood in representation theory. So for example, it exchanges in finite dimensional modules top and circle in a projective cover of a simple. Okay, so now the point is there is a second tensor product. And this second tensor product, which exists due to the fact that G is not monoidal, it defines a tensor product, and this tensor product is left exact. And it has a dual as a monoidal unit. Indeed, if I'm inserting here a dual and then I'm applying G, then I'm getting A, then I'm tensoring here over A, and you see I'm not changing anything. Yeah. So really this category of bimodules should be thought of as a category which has two tensor products. One of them is left exact, one of them is right exact. And in case you feel bored in the next few minutes, you can investigate this, the situation, and do the following exercise. Well, you see that this bimodule, a dual, which is not the monoidal unit, it appears in distinguished relations, namely if I want to use duality to put M to the other side and to have here the dual module. So, well, A star is obviously a very important object in the category of bimodules. And the category of bimodules is a monoidal category with two monoidal structures. So to convince you that this second monoidal structure is very useful, let's take a piece of algebra from the 50s. So Eilenberg and Watts, they investigated how in these specific situations with finiteness conditions, right exact functors can be written, and they can be written by a tensoring with a bimodule. Well, you see that if f is such a functor from A1 mod to A2 mod, then f of A is, because A1 is an A1 left module, that's automatically in A1 mod. But on the other hand, you see that the right multiplication acts by module endomorphisms. So the right multiplication gives, sorry, I should have written here A2 mod, gives automatically a structure of an A1 right module. And as a consequence, I have a canonical bimodule structure, and Eilenberg-Watts expressed, showed that for finite dimensional modules, you can express every right exact functor in terms of such a tensor product. Now, let me show that there is a left exact Eilenberg-Watts theorem, which is usually not mentioned in the textbook, but I think everybody knows that it exists. So suppose we have a left exact functor. Then by precomposing and postcomposing with our contravariant functor, I get from the left exact functor a total functor which is right exact. So I can write this right exact functor by the classical Eilenberg-Watts theorem in terms of tensoring. And of course, you have to be a bit careful. These are by this exchange, the G exchanges left modules in right modules, but I think that the principle is quite clear. Okay, and now you apply this to a right module. And if you substitute M, because dualization is anyway an equivalence of categories, by M twiddled by G of M, then you see that the left exact functor can be written in this way, but this is nothing but the left exact tensor product. And you see that the left exact tensor product gives again, an Eilenberg-Watts theorem. So Eilenberg-Watts becomes completely symmetric for left exact and right exact functors if you take into account that there are these two different tensor products. So, by the way, that's maybe not a main topic of interest to this audience. The category of bimodules is really, in a sense, the trivial example of a Hopf algebroid. In the same way as a ground field is really the simplest example of a Hopf algebra. Now, you can enhance the whole structure and convince yourself that really similar structure exists on Hopf algebroids, because Hopf algebroids are Hopf monads on categories of bimodules, and Hopf monads turn out to be friendly to these duality structures. So this is really a duality structure that appears in a lot of natural algebraic structure. And by the way, this whole Eilenberg-Watts thing can be also generalized, and you can look at this in a bit more abstract way. So you can start with right exact functors from some finite linear categories. You can show that this is canonically equivalent to bimodules. By the way, this is a delinear product. And you can, in the same way, show that left exact functors are canonically equivalent to this delinear product. And if you go through these equivalences, which are extremely explicit, then you get one big surprise, which is analogous to what I was showing to you. If you take A equal to B, for simplicity, you can start here with the identity. You go to some distinguished object here, a distinguished bimodule. It's actually, it can be written as a coend, but never mind. And if you go down here, well, the identity functor is exact. It's left exact, but if you go chase it through this diagram, you end up with a functor which is just a categorical generalization of the Nakayama functor. So that's the right exact Nakayama, and in the same way you get a left exact Nakayama. And so it means that if you're working with left exact functors, then you necessarily have the identity and a Nakayama functor. If you are working with right exact functors, you have the identity, which is a monoidal unit, and a Nakayama functor. So we have here a structure which calls for some axiomatization. And let me skip this part because that's probably not too interesting for most of you. Let me formalize now this duality structure. So we start with a monoidal category. And let me say that the monoidal category for the moment is not necessarily braided. Yeah, so I will make some comments about the braiding in a moment. Then we formalize the properties the dual of the regular bimodule has, and we say that an object is a dualizing object if for every y in C, the functor which sends the object x to this set, or well, in fact, we will be mostly enriched over vector spaces, is representable. So put differently, we have here a way to move y by taking a dual to the other side, but we don't do this here for the monoidal unit, but we do this for some other object. And this is called, so then G is called a duality functor with respect to K, and then a Grothendieck-Vertier category, or GV category for short, is a category together with the choice of such a dualizing object. And I should say here, there's an important difference, which in detail still gives us a lot of headache. If you have a rigid category, having duals is a property. And if duals exist, they are unique up to isomorphism. The choice of a dualizing object is a choice. And actually, you can, if you have a dualizing object, you can modify it by tensoring with any invertible object. So here, again, the invertible objects, well, the simple currents appear, if you wish. The dualizing objects are not unique, but they should be thought of as structure. And yeah, maybe I should make a word of a comment about history. So they start to appear under the name of star autonomous categories in the 70s. But back then, people were supposing that automatically the category should be symmetric. This was in a time where the braiding was not in everybody's mind. So one was assuming that the categories are automatically symmetric. I think these days we want to investigate both categories with a braiding and with no braiding at all. And I should also mention that this type of structure is very well known in a completely different field of mathematics. So there is a field called linear logic, and there people work with what they call linearly distributive categories with a negation. And just to give you a flavor why people in logic are interested in this, on one of your first days in university, you learned about sets and the union of subsets and the intersection of subsets. These are two monoidal structures, and these two monoidal structures have two different monoidal units. Yeah, so for the intersection, if you're intersecting with the whole set, then it doesn't change things. And for the union, you have to take the union with the empty set. And these two structures are related by taking the complement. And the fact that they are related, that there's a second tensor product, that they are related by a rule. Let me go back. Sorry for scrolling so much. Usually I try to avoid this. That they are related by a rule which is complement, and again complement. That's De Morgan's rule. Yes. So I'm just trying to convince you that nothing bad, nothing exotic is going on. It's a completely decent structure our professors should have told us about earlier on. But I didn't tell my students 10 years ago. Yeah, so you can blame me equally well. Anyhow, okay. So we have this, this structure here. And I've already highlighted that the choice of dualizing object is a structure. And these categories are extremely nice. So for example, you can show from the axioms that the tensor product is right exact. You can show that internal homs exist. So at right adjoints to the tensor product exists, and you have a very explicit formula for them. And it follows from the axioms that you have also a left exact tensor product, and whose monoidal unit is exactly the dualizing object. And then people have worked out quite a bit of theory. So for example, you can show that taking this duality functor twice is a monoidal functor, so it has a natural monoidal structure. You can introduce the notion of a braided Grothendieck-Vertier category. You can introduce the notion of a pivotal Grothendieck-Vertier category, which means that you are trivializing G squared, and there is the notion of a ribbon-Grothendieck category, and I should give a reference. There is a paper by Boyachenko and Trinfeld, where this whole theory is very systematically developed. And yeah, I should point out that this type of category seems to be friendly also to quantum topology. This is not a main concern probably for most of you, but you know that the fields are very neighboring, so it's a very encouraging sign. So Lukas Müller and Lukas Schweigert, they have shown that if you go to the bi-category of finite categories with the delinear product as the monoidal structure, and you look at a very natural algebraic structure, you take the little disk operand and you make it cyclic. Then the corresponding cyclic algebras are just pivotal Grothendieck categories. And if you do this not with little disks, but you do this with framed little disks, then you get ribbon-Grothendieck categories. So this means that if you're doing algebraic structures in finite tensor categories, then with respect to very natural operands, every topologist will like, you are automatically ending up with pivotal Grothendieck categories or ribbon-Grothendieck categories. And indeed, by using a lot of technology, they have the really impressive result that ribbon-Grothendieck categories lead to representations, well, unfortunately not of mapping class groups, that's not yet there, but of Handel body groups. So these are those subgroups of mapping class groups that extend over a Handel body. So if you think about the modular group, which is the mapping class group of the torus, right? Then the Handel body group doesn't sound particularly impressive, because if you have a solid torus, yeah, then you can cut the torus and do a Dehn twist, but the other Dehn twist doesn't work. There is only one order 2 element more than just a single Dehn twist, but on the Riemann surface of higher genus, this is still roughly a square of the mapping class group. So the structure seems to be friendly to quantum topology, to mapping class groups, although we don't understand what additional structure should guarantee that you get, in fact, representations of the whole mapping class group. I mean, this is an obvious research problem, but I promised you to show you open ends and existing puzzles. Yeah, so yeah, good. So let me now try to convince you that if you are looking at vertex algebras to which you can apply the HLZ theory of tensor products, you naturally get such a Grothendieck category. And let's be honest, we didn't do too much work. We have this very long theory in several hundreds of pages, and it was just a way to look at these hundreds of pages. But I mean, that's what category theory is made for, that you look at things in a way that you understand it in few words. And it doesn't, of course, make their work unnecessary. So let's take such a vertex algebra, and I'm not going even to recall what the conditions are, because that's not the point of this talk. We have to be sufficiently careful that we has a grading, so maybe an additional grading in such a way that you can decently dualize. So think about a grading by a root lattice. And if you have a root lattice, then you know that if you want to do decent examples for the modules, you should allow for a bit of a finer grading by a weight lattice. So that's why we have this situation of 2 abelian groups. And as usual, you have to go to a nice class of modules, and a nice class of module means that the HLZ theory applies and that the homogeneous components are here finite dimensional, because we don't want to mess up with structure that's already complicated at the level of vector spaces. Yeah, so that's 2. So then it's very natural to take the grade-wise dual, the contragradient module, take in any finite dimensional homogeneous component, the vector space dual. It can be endowed with an action of the vertex algebra, and this is done as usual. You do the pairing of a linear form and a vector. You explain how to act on the linear form by explaining how to act on the vector. And the important thing, and this is a formula that's from HLZ, is this dual action has the Virasoro algebra entering. So this is important. So the conformal structure of the vertex algebra enters. Right, that's the, so you know that interesting vertex algebras have different conformal structures, so the notion of duality will depend. And that's already a nice fact. Recall that Grothendieck-Verdier duality was structure, it wasn't a property. So just, we will have different dualizing objects in the end here. So the contragradient is involutive, and then the contragradient of the vertex algebra itself is not necessarily isomorphic to the vertex algebra itself. It's imposed as a condition in quite a few papers, but let me argue that very important examples for mathematical physics force us to pay some attention also to the case where the contragradient of the vertex algebra is a different module. So I think the ultimate theory of vertex algebras will need to take care of this case as well. So just a brief sketch why this appears in these models. So how do you get them? You take the Virasoro-Verma module. You take, in a sense, the boring case, H equal to 0 and C equal to 0. So Virasoro central charge is 0, and the eigenvalue of the Virasoro zero mode is 0. And this Virasoro-Verma module has 2 linearly independent null vectors. Well, if you mod out all null vectors, it's a bit boring. You get something, the quotient is a vertex algebra, but it's a bit small, right? On the other hand, we do not have a choice whether we mod out N1 or not, because we want to keep translation invariance. So if you only mod out N1, then you get a vertex algebra, and now some technical business. I mean, we are always working with categories that have certain finiteness conditions. So we have to extend this. This can be extended. I think people who have worked on SL2 related structures will not be surprised to find the word 3 here. And you get in this way a vertex algebra which has a simple quotient and which has a simple submodule. So the vertex algebra here, and this is actually the vertex algebra that's in some way also relevant to study percolation in mathematical physics. Or it's a relative of the vertex algebra that should be relevant for percolation, is a vertex algebra where when I'm dualizing the role of W0 and W, and there should be, sorry, there's a there should be a 0 here, of course, are exchanged. So they have the same character, but the representations are not isomorphic. And some of you will know that almost the same formula are in Simon Wood's PhD thesis 10 years ago. So really, we are kind of bringing some old results in a standard framework. That's what this talk is about. I should also point out, but probably you're more aware of this than I am, that the contract gradients already enter in the very construction of the HLZ tensor product. Because what you do for the HLZ tensor product is you study the algebraic dual, you study inside a subspace, and then you take this subspace and you do the contract gradient dual, and that's what you call the HLZ tensor product. So you could even pretend that this dualization is natural for an algebraist because you want to end up with some right exact tensor product which behaves like the tensor products we know in algebraic structures. But if you extract the very structure from conformal blocks, and that's what in a sense the HLZ construction does, then the left exact tensor product is more or less there in a certain disguise. Yeah, so namely here the dual of the tensor product is defined not as a quotient but as a subspace. That's the point I want to make. Okay, and then you look at HLZ and you are very happy, and you find indeed that they produce isomorphisms of chiral intertwiners. Chiral intertwiners are, of course, the spaces that capture the homes for tensor products in the categorical setting. Yeah, and if you look at this, you see that if you take here such a tensor product and you insert for M3, you insert here the contract gradient of the vacuum module of the vertex algebra is seen as a module over itself, then M3 will go down here to M3 dual, but this here is just the vertex algebra while X stays, and this module will go to the other side, and you get exactly this relation which tells you that the functor of taking the contract gradient dual is given by evaluating tensor products into the dual of the vacuum representations. So you see, if we write here a theorem, well, we didn't do the work. The result is really in HLZ. Yeah, and yeah, so you can illustrate this, and I will be it will not go in too much detail here. If you think about a vertex algebra where you have a family of conformal vectors, then probably the first thing that comes to mind is you will think about the Heisenberg vertex algebra. Let's base it on some vector space, but it could be one-dimensional. And then you can, this is here, in a sense, the standard conformal vector, but you can shift the conformal vector. Some people call this the Feigin-Fuchs boson. And then you see there's a family of vertex algebras. Let's compactify this on a lattice, not because other things are uninteresting, but because we are very much used to finite categories, and I don't want to quit this framework, but obviously there's a more general story. And then you know that the representation category is given by the dual lattice modulo the lattice. Of course, if I say lattice, I should have added qualifiers such that this is a finite abelian group. And then you get a semi-simple braided fusion category, which a fusion ring, which is just a group ring of the abelian group, and all objects are invertible. Now, I told you that if I'm given a dualizing object, I can tensor with an invertible object, I get again an invertible object. So essentially, all these objects qualify as dualizing objects. And so you go through the details, and well, actually, we want to have a bit more in this context than just finite tensor categories. We want to have written tensor categories, and it is not automatically written, but actually the number here has to be a square. So only every second object is a dualizing object such that there is a written structure, but that very nicely fits explicit calculations in the vertex algebra. Yeah, so the point is, if you're working with Huygens-Fuchs boson, so if you're working with background charges, then you're more or less automatically, at least at some intermediate steps, in the realm where you have more general dualities. And of course, this extends. You can construct from these vertex algebras a lot of other vertex algebras, and unsurprisingly, you will have similar structures for ghost systems. But let me now tell you why. So up to this point, and that's for the theory of vertex algebras, you are quite happy at this point, and you hope to use as much of the mathematical literature as possible. And actually, I want to use the last 10 or 15 minutes to tell you why our happiness somehow faded a bit. Because actually what you want to do is you want to construct a topological field theory that's a local topological field theory, a full CFT, in which you combine left movers and right movers. And well, I've spent repeatedly time in the last 20 years to think about this problem. So I thought, okay, now we have the ultimate framework where you should ask this question. So this must be very nice now. But there are a couple of really big problems. So what we want to construct are things like boundary fields, bulk fields, obeying modular invariance, OPEs, and all this stuff. And here the problems start. So the first thing is, for the representation category of a vertex algebra, you expect that the braiding is non-degenerate. There are various notions of non-degeneracy for braidings, and in the case of finite tensor categories, Shimizu has shown in a beautiful paper 5 years ago that they all coincide. The paper heavily uses rigidity. It's not clear how this behaves in general. That's open. On the other hand, the fact that for a non-degenerate braiding, we can replace left movers paired with right movers by the Drinfeld center. That's very important for the type of theory we have been developing in the past 2 or 3 years. And actually, I think one needs a better understanding. And one of the questions I would like to discuss with you after the talk is, the Drinfeld center is a very natural object in the theory of finite tensor categories, say, and beyond. I'm not sure I've seen a lot about the Drinfeld center in the context of vertex algebras. So if you can explain me why this is true, or whether you know anything about the Drinfeld center in the context of vertex algebras. I'm really interested to hear your thoughts. So that's one point. If you define the Drinfeld center naively, then you get really strange behavior. So for example, if C is finitely semi-simple, then it can happen that the Drinfeld center in the naive definition has even infinitely many simple objects and is non-semi-simple. So somehow all these permanence properties that semi-simplicity transfers to the Drinfeld center, that hinges on rigidity. So it's not clear whether the Drinfeld center is still the good notion. And also, if you want to handle the forgetful functor from the Drinfeld center to the underlying category, then in handling its adjoints, you very explicitly use that the duality, that rigidity is op-monoidal. And here we don't have op-monoidality. So also this is gone. Yeah. And then the next thing is, in this whole business, the additional data on how to combine left movers and right movers, that's now known for more than 20 years, is really a module category. So that determines a modular invariant partition function. The theory of module categories over Grothendieck-Verdier categories is not developed. And even if C is finitely semi-simple, you can have infinitely many inequivalent, indecomposable module categories. So these finiteness properties are gone. Even worse, we don't know how to define decently a relative delinear product, and implicitly we don't have any Morita 3 category where we use bi-module categories and all this beautiful stuff. It all hinges on rigidity. And if you take the famous EGNO book, so this book by Ettinghoff, Gelacki, Nikšić, and Ostrich, and you try to rewrite it without using the word rigid, well, your book will be much thinner than theirs. Yeah, so that's now this is in principle bad, because all this structure plays very nicely if you have rigidity. And what I want to show you just is to what extent, as what type of structure you want to have and what you get in the Grothendieck-Verdier case and what you do not get. So what you want to do is you want to feed in a module category. And then, well, the objects in the module categories have, by the way, they have a very direct interpretation. They are boundary conditions. You want inner homes to describe boundary fields. Grothendieck-Verdier categories have inner homes. That's nice. The OPE you expect to be the composition of inner homes. Well, inner homes have compositions almost by definition. That's not critical. But you also want that the inner home is, well, the inner home, the inner end is an algebra, but to construct things decently, you want to be able to put here the word Frobenius algebra. And a Frobenius algebra is an algebra which is an algebra and a co-algebra. You get a co-algebra by using a dual concept to the inner home. The inner home is the right adjoint of a right exact tensor product. You can take the left adjoint of a left exact tensor product. This is what people call a cohom. And the cohom of end MM is a co-algebra. But here, the hom is for one tensor product, the cohom is for another tensor product. So somehow this naive pattern of looking for Frobenius algebras doesn't work in the doesn't work in the Grothendieck-Verdier case. That's one more challenge. So this identification technically means that we are looking for pivotal module categories. This is something that's extremely well understood now for the rigid case, and where we are completely in the dark for the non-rigid case. What's also very well understood is how to get Frobenius algebras in the Trinfeld center. And well, also this breaks down. So for example, the categories of module endofunctors are in general module categories over the Trinfeld center. But we cannot prove anymore that they are rigid, that they are pivotal, if we do not have rigidity. In the rigid case, we have extremely nice theorems, so we can control this category very well. We can compute its internal home, and the internal homes are really decent candidate for bulk fields, and actually they are better than candidates. They reproduce the bulk fields in all known cases. But if we don't even know what the Trinfeld center should be, then or what the replacement of the Trinfeld center should be, this whole theory, which is something we are extremely happy about, doesn't simply extend. So that's why I really want to ask you, do you have any replacement for a Trinfeld center in the case of vertex algebras or representation categories of vertex algebras in mind? Because adding a half braiding is something which you wouldn't do on the representation category of a vertex algebra. It's a very ad hoc categorical procedure. Yeah, and yeah, so in this setting, you can, so with rigidity, you can work extremely nicely. So if you want to describe defect fields, even for defects that separate different local CFTs, then we know how to describe the defects. We describe them by right exact module functors, and then we can describe them by these relative homes in the category of module functors. And actually, this gives you correct objects in the Trinfeld center, which by this thing, which again uses rigid, is a combination of left movers and right movers. Well, actually, this can be worked out in much more detail. You can find explicit formula for them, which in a sense generalize the formula that you have for the Cardic case, in the semi-simple case that you are summing over all objects and dual objects, so the charge conjugate partition function. Yeah, but for the moment, we don't have this in the Grothendieck-Verdier case. We have in the rigid case, we can show that many important consistency constraints are obeyed simply by identifying all OPEs with structure morphisms of categorical objects and using their universal properties. Well, this works actually up to genus 1 relations. Genus 1 is hard in any setting. But again, for Grothendieck-Verdier, we don't know. So let me conclude, therefore, with the statement that we need to understand better the categorical properties of the Grothendieck-Verdier categories arising as representation categories of HLZ vertex algebras. They should be nicer somehow. They should be nicer to allow these for these constructions. They should also be nicer, coming back to this remark about the Müller-Wolke paper, to give us not only representations of Handel-Body groups, but even of mapping class groups. Well, potentially projective representations. We are aware of this, of course, yeah. But they should be nicer. And this understanding this would be singling out an important class of, and here I should really say, of Ripon-Cohen Quartier categories. And getting this notion would really kind of be the framework to deal with finite conformal field theories independent of semi-simplicity. And obviously then, so we have to go beyond these finite tensor categories, which unfortunately by their definition, finite includes rigid. Yeah, so that's too restrictive. And of course, we have to investigate the whole theory of module categories then. The notion of an exact module category that's so important in the EGNO book, that doesn't directly persist. And so, yeah, I think that's a point where for the vertex algebra community, it is good to study also vertex algebras which are not isomorphic to the contragradient dual, and try to look out for categorical properties of these representation categories, or of, yeah, and on the other hand, categorical insight might help to deal a lot, to organize a lot of these representation theoretic structure. And this is the summary of this talk. Thank you very much.
Thank you so much, Christoph. Let me stop the recording so that we can